Hi everyone, welcome to Chapter 2, Video 3, which is about the first half of Section 2.2 in the Anatomy and Physiology textbook. We have three goals for this video. First, we want to be able to distinguish between mixtures and compounds. We want to understand some of the properties of water that are important when we talk about physiology. And then we want to be able to differentiate between the three types of mixtures. So first of all, a mixture is anything that is physically blended but not chemically combined. So there's no chemical reaction taking place. If we use different techniques, we would be able to separate the things back out into their component parts. Most of our body fluids are mixtures of chemicals, and water is very important when we talk about mixtures. Depending on the body fat that a person has, humans are made of between 50 and 75% water. So understanding how water works in mixtures is really important as we understand physiology. So we're going to jump right in here and talk about water. Water's first important property is its ability to dissolve other chemicals in it. We call water the universal solvent because so many different molecules are able to dissolve in water. If something can dissolve in water, we describe it as hydrophilic. Hydro meaning water, philic meaning loving. So molecules that are charged in particular, or polar with a difference in charge between the two sides of the molecule, tend to dissolve very easily in water. Things that don't dissolve in water we call hydrophobic, and these are things we can think of like fats and oils. These are things that are nonpolar or are neutral. So this is something that we talked about in a previous video as well. Remember that we said the ions of sodium and chloride tend to make spheres when they're in aqueous or water-filled environment. So in this case, our positive sodium ion is making a sphere where all of the water molecules want to line up with that partial negative charge towards the sodium. And over here, where we have the chloride with its negative charge, all of the water molecules want to line up with their partial positive charges on the hydrogen sides close to the chlorides. So water has the ability to overpower the attraction between the positive sodium and the negative chloride. Adhesion is when two things tend to stick together, and water demonstrates this property when membranes, especially in the abdominal cavity, are kind of lubricated by water, and so the friction around those organs is less, and they don't rub against each other and cause damage. Cohesion is the opposite. It's interesting that water has both of these properties simultaneously. So cohesion is when the water molecules tend to stick together. And if you've ever done the little thing where you drop water one by one onto a penny and the water forms a dome over the top of the penny and doesn't spill off right away, that's surface tension. And that surface tension comes from the hydrogen bonds, like we were talking about before. And this is really important as blood moves through capillaries, for instance. Our next important property of water is reactivity. So water is able to do a whole wide variety of chemical reactions. Two that are really important for us are hydrolysis and dehydration synthesis. So hydrolysis happens when water is used to break a molecule into two smaller parts. Hydro meaning water, lysis meaning breaking. Dehydration synthesis happens when two molecules are joined together and a water is removed in the process. So dehydration is the removal of water, and synthesis building a larger molecule. water has a really high heat capacity, and that means it takes a lot of energy to increase the temperature of water compared to other liquids that we can think of. So when we talk about a calorie, like a calorie that we might measure the energy in food with, what we're saying with 1 calorie is equal to the amount of energy, the amount of heat energy specifically, that it would take to raise 1 gram of water by 1 degree Celsius. Okay, so something, let's say a slice of pizza, has lots of energy stored in it. If we were to burn it efficiently, we would be able to raise the temperature of 1 gram of water much more than if we extracted all of the energy from, say, an apple. It's the hydrogen bonds between the water molecules that allow for this property. And it's really important when we consider that humans and other warm-blooded creatures need to keep an internal body temperature that's very consistent. So now we're moving on to the difference between solutions, colloids, and suspensions. So a solution is a solute mixed in a solvent. The solute is the thing that there is less of that gets mixed into the solvent, the thing that there is more of. Okay, so the real simple example that I always like to give for this is think about making Kool-Aid. Okay, so your solvent is going to be the water, and then the solute is going to be the sugar and flavor and color. And when you mix it all together, you get a solution. And the solution has certain properties. First of all, the particles in a solute, the thing getting mixed in, the solute, are less than 1 nanometer. The solution looks clear because the particles don't scatter light. It'll go through most membranes, and even if you leave it sit, it does not separate. Okay, your Kool-Aid isn't going to separate into different phases. The solute, the thing getting mixed in, can be a gas, a solid, or a liquid. And we usually think of the solute as being a solid, the sugar, the flavoring, the coloring. But it doesn't always have to be. If you have a Coke or a Pepsi or a Sprite, the bubbles of carbon dioxide in the Coke is a gas. The carbon dioxide gas is the solute, and the liquid portion is the solvent. Liquid and liquid could be food coloring into a glass of water. Okay, so this is a nice depiction of how we can differentiate between a solution, a colloid, and a suspension. We'll talk about colloids and suspensions next. So colloids have a slightly larger particle size, and because of that larger particle size, they look cloudy. So think of milk, for instance. The proteins and sugars suspended in milk are a little bit larger. They're going to fall in this range here than table sugar and flavor that we were just talking about with the Kool-Aid. Milk has a cloudy appearance. You can't see through a glass of milk. So colloids, when we talk about anatomy and physiology, they're often proteins that are in the water. And finally, a suspension has particles that are larger than 100 nanometers, so even larger than we saw in the colloids. They're also cloudy, cannot see through them, they're not permeable to light. And the distinguishing factor here is they'll separate if you leave it to stand. So if we have a whole blood sample and we leave it just to sit undisturbed, the red blood cells will sink to the bottom and the plasma will stay at the top because the red blood cells are more dense than the plasma, and the red blood cells exceed the particle size, and so they don't stay in the suspension. So that's a little bit of background about mixtures, and I'll see you back here for video 4 in just a moment.